So welcome. So we're going to go to this next section, which is AC theory. So what we have here is, first of all, there's two ways of representing an alternating signal. AC theory, AC like it comes out of the wall socket. If it's generated by a moving coil inside a magnetic field, you get a sinusoidal signal pattern. The voltage is sinusoidal, and etc. Okay, that's fair enough. I can represent it by a continuing wave, like we did in the oscillation and wave section. There's a repeat, which is every period. There's a repeat, and we can talk about the frequency of it. We can talk about the amplitude of it, just like we did with oscillations and waves. The other way is I recognize that because it is a repeating pattern, I can represent it like it's a phasor, which means that it basically, this point here corresponds to the beginning, and then I'm here, which is a quarter of a way through a wavelength, which is a quarter of a way around my circle, and then I'm here, which is half a way through my wavelength, which is halfway around my circle, and then I'm here 3/4 of the way through my wavelength, which is 3/4 of the way through my circle, and then I'm back here at the end of the first wave, which is the beginning of the second, so I'm back at the beginning. Yes?
Does that A correspond with that A?
So, there's a mistake in this.
Oh, okay.
Well spotted. And that is that all I do is I take the y-axis component, and the problem I find is that that A is there. It's before I got to the peak. So the A is wrong. And it wasn't a deliberate mistake, I just drew it wrong. And then the B is that bit there, which is the same as that bit there, and the C is that value there for the voltage, which is that value there, and there's the D, and so on. They both got utility, yes.
Isn't it just the same as the unit circle?
Unit circle, yeah, I guess it is. Yeah, I suppose so, yeah. So I need a function that describes what the voltage is in time, and so the voltage is Vmax, whatever the amplitude is, sine omega t. Sine because I started off with it being 0. I could have started off like that, in which case it would have been a cosine function. The sine or the cosine depends on where I choose to start. I got to remember that omega equals 2 pi f, so I can convert from omegas, radians per second, into hertz. Yeah, no big deal. But the phasor has utility, and that's why it's in the textbook. So we'll deal with the phasor in a bit. Problem. If I take my AC voltage or my AC current, depending on what I want, and I want to find an average value to avoid this oscillation, I want to characterize it somehow. If I choose the average value to characterize my wave, I'm going to end up with a huge problem, because it spends as long being positive as it does being negative. And so the average current in this particular graph is 0, because we have as much positive as we have as much negative. So the problem with that is also 0. And that is also 0. As well as that is 0. So anything, basically, as long as it's symmetrical, comes out to be 0. Which means that taking the mean the average is meaningless. It just doesn't work. And the problem is that the negative bits are cancelling out the positive bits. So we need to find a way around that. And the traditional way around that is you squared everything, so you got rid of all the negative bits. They all became positive. So you square everything. And then to get rid of the curviness, we do the mean of that, so we get a nice steady value. And then we recognize that this steady value is great, but it's too big because we squared everything. So we square root that steady value. So let's have a look. What we did, we squared it, and we rooted it, and we meaned it, and we rooted it. And so they call this the RMS, the root mean square. I don't know why they don't call it the SMR, because that's the order you did it in, but it's called the RMS. The RMS is 1 over the square root of 2, which is 0.71. So I remember it as 71% of. You know. So we say if I want the root mean square current for a sinusoidal curve, it has to have this shape. It has to have the nice sinusoidal shape or cosine shape, but it can't be some wacky, it can't be a sawtooth or something like that. It's got to be this nice shape. Then it's basically 71% of I max. If we have a voltage, it's going to be 71% of the maximum voltage. And here's the payoff. If I have an AC source feeding a resistor, and I say, what's the power dissipated in that resistor? I've learned that power is equal to my voltage times my amps, yeah? I learned that in DC. Does it still apply for AC? If I say delta V equals IR, I learned that for DC. Does that apply for AC? Yes, it does. But it does with some specification. I can use my maximum current, and that will give me my maximum voltage. Or I can use my root mean square current, and that will give me my root mean square voltage. But if I try to use my maximum voltage and my maximum current, I don't get the maximum power. I get a crazy answer. Because it's only at the Vmax, and it's only at the Imax for an instant. Most of the time it's less than that. So, although with Ohm's law I can use peak current, peak voltage, or I can use RMS current, RMS voltage, with power I got to be in RMS. Using the peak values makes no sense whatsoever. So power is equal to delta V RMS times I RMS. This is peak for AC. So I've got to be careful about that. Got to be careful about that. An AC current has an amplitude of 10 amps. What is RMS? IRMS is equal to I max over the square root of 2, which equals 0.71 I max, which equals 7.1 amps. AC EMF has an amplitude that, so VRMS is equal to V max over root 2, which equals 0.71 of V max, which equals not 7.1, but 7.1 plus 3.55, which is 12.65, I think, volts. Is that right? 0.71 times 15. I think that's right. Yep. Cool. Know those. 10.65, okay. Yeah, 7 plus 3, yeah, thank you. 10.65. Now we do the main bit. I'm just going to talk you through it. So next time when we come, you'll have an idea where we're going. What we're going to do is we're going to look at each component in turn in an LRC network. Because something weird happens. When I get an oscilloscope, and I look at the voltage across a component, and I look at the current through the component, and I see when is the maximum and when is the minimum. With a resistor, I get the maximum current when I get the maximum voltage. They are in phase with each other. I can represent it like this on a graph, or I can represent it like this on a phasor, where this corresponds to that. I picked those 2 points there, and I drew them here. They both have the same angle to the starting point because they're like in phasor space. They are in phase with each other. What phasor space means is how far are you through your cycle? And, you know, if I'm near the beginning, I'm here and there and there. So imagine going through the cycle in like slices of a cake. And then what are my two sizes? And these two, you know, at this 90-degree point, one of them is going to be there, and one of them is going to be there. So I can draw one as one line and one as the other line in here. It's a way of keeping track, yeah? In phasor space, there's no phase shift between the current and the voltage in a resistor. When you get the maximum current, you get the maximum voltage. Well, when you get the maximum voltage, you get the maximum current, yeah. And I can say for this, I is equal to delta V over R. There's my, you know, Ohm's law, good old Ohm's law. When I try to do the same thing with an inductor, what I find experimentally is things don't look the same. I don't get the maximum current when I get the maximum voltage. That's a bit weird. But it comes out of the fact that I have a di by dt term in there. And in fact, when I look at phasor space, I see my voltage is leading my current by 90 degrees. So it's in front. I'm not going to justify it here, but I can then make up, create a thing called reactance, which is like resistance. Mathematically, it does the same thing. I equals V over R. Oh, omega L is like my R. Let's call it XL. So there's going to be a new term called reactance, which is doing the same job as resistance. Same units, same everything. Don't know why they didn't call it inductive resistance, but they didn't. I guess because an inductor has a resistance, which is different. If I do the same thing with a capacitor, again, I find that the maximum current does not come when there's the maximum voltage. But here I find that my voltage is now in front of the current. Sorry, my voltage is behind the current. So that was, whoops, daisy. That was in front, this is behind. Now that's interesting, because what that means is that when I put these three components in series, at any instant in time, the potential difference across my inductor is in the opposite sense to my potential difference across my capacitor. It's not that I can't add them up arithmetically because they're in different phase space. They're pointing in different directions. So I can't just arithmetically add them up. I got to vectorially add them up. And in doing the vectorial addition, I find that the voltage drop across the L is directly opposite in terms of the sign, the positive and the negative. It's in the opposite sense of the voltage across the capacitance. So they're fighting each other. That's very strange. You can't see it very well here. This is, you know, 3 voltages and, you know, there's some weird stuff going on, but what we get is we get to stuff like this where we start trying to add up our voltage across my inductor and the voltage across my capacitor and the voltage across my resistor. And what I find is, because of this, I get my inductive reactance and my capacitive reactance and my resistance. And I can work out a impedance for the entire circuit. And what I'm going to find is that for any given circuit, because the reactances are frequency dependent, for any given circuit there's a frequency at which the reactance of my inductor cancels out the reactance of my capacitor, because they're equal and opposite. And I end up with this sweet spot where I get a minimum in my resistance, which is a maximum in my current flow. And that is the tuning point in your circuit. That is the part of your circuit that's like, this is where my radio station is. So that's the analysis. We're going to go and do a bit on quality factor, and then we'll do a bit on transformers, which is different again. So next time we're going to look and we're going to try and step through this so that we kind of follow what's going on and follow the math. And we'll get there.